All right, so basically, we'll be talking about latent semantic analysis, and we'll be talking about certain problems that it has and how we proposed extension to basic latent semantic analysis to overcome these syntactic blindness problems. So the outline, I'll just introduce what we've done, what latent semantic is, a quick introduction to that, then what was the problem, and what we've done for it, and then discuss the experiments and results, and finally conclude. So basically, natural language processing is concerned with the techniques of understanding and generating natural language by machines. So, and specifically, we have natural language understanding and natural language generation, which are the two subfields of natural language processing. And in natural language understanding, we try to analyze the language to produce meaningful or semantic representations. And semantics here relate to the meaning of a word or a text or a phrase or text, which basically uh, encompasses lexical semantics, which is the analysis of word meanings and the relations between them. So basically, the natural language understanding tries to make natural language understandable to machines so that machines can use natural language constructs and basically which can be used in different forms of searching and information extraction. So understanding this meaning or the semantic of a text or a sentence, it allows machines to look for similar or semantically similar sentences or text. And as we know that the internet or the web right now, or the semantic web as we call it, is basically ever growing, and we've got so much of information available now that is obviously almost impossible for humans to take care of by themselves. So we can definitely use machines and to actually get a better understanding of all this dispersed information. And this is where natural language understanding can play a very important role. So as I said, semantics relate to the meaning of a text or a document. So many techniques have been proposed. Currently, more neural network based techniques are proposed, have been used, but latent semantic analysis is basically a traditional technique which basically uses which computes the semantic overlap between different pieces of text. So given uh, a corpus of different texts, it can actually learn the representations of different words, and it can actually learn where the context in which different words occur. So the main concept or the underlying concept of latent semantic analysis is that the meaning of a text is related to the existence and non-existence of distinct words. So words with similar meaning will occur in a similar context. So that means that if we've got two documents and they are about the same topic, then there is a high probability that the words that occur in document one will also occur in document two, because they're talking about the same topic or the same, and they should convey the same meaning. So latent semantic analysis uses SVD or singular value decomposition on a bag of words model to generate document and term vectors for each text. And then we use cosine similarity or other similarity measures to basically evaluate the similarity between these vectors. And that gives us the total similarity between two different textual documents. So far so good. Natural language understanding gives us machines the ability to understand text, and we've got many approaches, and latent semantic analysis is one of them which has been successfully used. But there are certain problems with latent semantic analysis, and which I've just listed here. Basically, the first and foremost is uh, latent semantic analysis ignores the syntactic composition of sentences, which results in a high similarity score between two sentences with completely different meaning. This kind of seems very counterintuitive, but basically because uh, latent semantic analysis is only working on the premise that words that exist in the same context convey the same meaning, that means that two different documents that talk about different topics but with similar words can also have a high correlation between them. Secondly, LSA does not consider the relationship between the subjects and objects during a sentence comparison. For example, if we take the sentence, the boy stepped on a spider, and another sentence, the spider stepped on a boy, these are given a 100% similarity, semantic similarity score by LSA. And we can clearly see that just by changing the subjects and the objects, the complete meaning of the sentence has changed. The third problem, LSA considers a list of words without having a proper sentence structure as a complete sentence or a complete thought, which basically means that a person, or if we've got two different documents, one has a complete sentence in it and the other only has a list of words or keywords in it, it basically matches that and thinks them to be semantically similar at 100% level. This can be good for online searches, but when we talk about implementing latent semantic analysis for automated grading systems, then this can really be counterproductive because a student might provide a list of words, doesn't provide a proper English sentence, and just gives a list of words which might even be considered as a proper answer, or which might be graded as a good answer even though the student did not make any sentences and just wrote a few keywords. And finally, latent semantic analysis cannot differentiate between two sentences that are semantically related to each other but have a negation in them. And an example, like Christopher Columbus discovered America and Christopher Columbus did not discover America, again, they get a more than 90% semantic similarity score because of similar words occurring in a similar context, but the not or negation word in the second sentence completely changes the meaning of the second sentence, and hence the meaning of these sentences are not the same anymore. So what we proposed for this is XSLA, which basically stands for Extended LSA. Basically, it is an algorithmic extension where we basically are extending the traditional latent semantic analysis implementations, and so it can be used with any other LSA implementation that exists to complement the results. Our approach basically adds syntactic information to the terms in the documents, and which is basically then used to complement the results of the LSA comparison. XSLA adds the following syntactic markers, the parts of speech tags, and a sentence dependency structure role that specific words play within a document. So this semantic enrichment added by XSLA basically enhances the term matrix, which is used to compute similarity scores. And in our results, we see that the final similarities, semantic similarity scores that we get are much closer to what they really are in real life. So basically, the XSLA approach has been developed so far for the English language sentences, where each sentence has one independent clause that contains a subject, verb, and a complete thought. English language follows the SVO structure, which is the subject, verb, object structure. So we always have the subject, which is followed by a verb, and then it is followed by another object that the subject is basically performing some action on. So we've basically divided XSLA in two phases, which is the pre-processing phase and the evaluation phase. In the pre-processing phase, we basically collect the different language markers, for example, parts of speech tags, the sentence dependency structures, and the composition to basically map or tag all of these words or tokens within the text to their specific parts of speech tagger or sentence dependency structure role. And then this information is passed on to the next evaluation phase, where each token is then compared to the other based on that meta information that we've added to that specific token. This allows for more robust evaluation and comparisons, and that basically improves the performance of basic as latent semantic analysis. So for our experiment, what we did was we took 200 sentence pairs from the Stanford Natural Language Inference corpus, which has been normally used for such kind of natural language understanding tasks, including subject-verb agreements and semantic similarity tasks. We applied both simple LSA and the extended LSA on the same test set and recorded the semantic similarity scores produced by each. And to compute this similarity score, we basically used an online API. So for the simple LSA, we simply sent the two text documents, and with uh, our extended approach, what we did was we created the matrices and then sent them word by word instead of sending the whole document, so that we get a better comparison result. So for simple LSA, the complete sentences were passed directly, said. So here a graph shows the results that we achieved with our comparative experiment. XSLA is shown with the red line, and the blue line shows the simple latent semantic analysis. And if you can see that the first few sentences, latent semantic analysis is giving 100% score, whereas the difference in XSLA is very clearly visible here, and it gives or scores them very low, whereas latent semantic analysis gave them a 1 score. And if we see an important thing is every time latent semantic analysis score is down, XSLA also follows the same trend, which means that XSLA is also able to converge to the point where it matches latent semantic analysis, basic latent semantic analysis results when two text pieces are not semantically similar. And then it is also able to provide better results when both the text pieces have similar words, but they are actually semantically on a different level. So here we show some more examples of simple sentences. For example, here we see the first sentence: the earth must revolve around the sun, and the sun must revolve around the earth. Now, if we see they have the same number of words, but the objects and verbs, the objects and the subjects have changed positions, which obviously mean that the whole sentence meaning has changed. Latent semantic analysis gives it a score of 1, whereas extended latent semantic analysis gives it a score of 55. For our threshold, we've seen that any score below 75% means that the sentences are not really close to each other. Please remember that we are doing this in the context of automated essay graders or automated answer checking. So anything with any answer to a question where the answer must be the earth must revolve around the sun and the sun must revolve around the earth is the answer that we receive, then it should not be considered as a correct answer. And any score less than 75% is not considered as a correct answer for our system. Similarly, we can see more examples. Money cannot buy happiness. Again, all of these latent semantic analysis straight out gives a score of 100% similarities, whereas our approach, if we can see, on average always gives it below 50%. And yeah, so basically, latent semantic analysis is a corpus-based approach which computes similarity of text with corpus using algebraic techniques. And basically, it has been shown to work, and it has been used extensively in systems, especially grammar checkers and automated grading systems and semantic search engines. So as we've seen that it only takes or considers the surface level features, which are the tokens or the words, and it does not consider the syntactic implication of these words and the roles that they play in a sentence. And due to that, we say that latent semantic analysis is syntactically blind. And for this research, we've tried to enhance latent semantic analysis by introducing our algorithm, the extension, which basically uses parts of speech tags and sentence dependency structure to get the positioning of the tag, the role it's playing in that sentence, and use this meta information to enhance the term matrix within the latent semantic analysis, which has given us very good results. And at the moment, we are trying to improve the technique so that it can handle more complex sentences, because right now, initially, we've got simple sentences and compound sentences, but there are more sentences that in English that actually have more complexities. And so, yeah, that's our research. Thank you very much. I'll be open to any questions you have.
Thank you, Doctor, for your presentation. Do you have any question?
Hey, hi, this is Winnie from Hong Kong. That's a very interesting research. Just want to ask, like, first of all, is that sort of like only applied to English or else Latin languages as well? Secondly, how is actually the application of this one?
Yeah, thank you for your question. At the moment, just we've only done this for English language because the corpus that we've used was trained on English language. So at the moment, it's only covering the English language. And as I said, our focus at the moment was on improving automated essay graders and short answer graders that can be used on that are basically used in specifically systems like intelligent tutoring systems or online e-learning systems. So when we have questions on e-learning, on online learning systems or e-learning systems, we try to have short answers from students. So any technique that can basically give us results, because we've also checked it with neural network implementations like Google's universal sentence encoders, and they also seem to have the same problem, that because most or almost all of these techniques rely on the concept of statistical analysis of data, that the words in a corpus, how they're positioned and where they're positioned and the context they're positioned in. So basically, they sometimes forget or leave behind the syntactical information, and they are not learning that unless and until they're made part of that specific corpus. So we've also tried to experiment or compare our results with that of the USA, and we've found improvements in the sense that at least our algorithm or our extension can flag certain values, or can at least provide extra information to authors or developers of these systems that can make use of that information to enhance the results of the semantic similarity that they've produced.